So the idea of related rates is we may have some function y. And y could be in terms of x or anything else that we need. But what we're looking for is y as in respect to time, or the rate of change over a given time period. Examples of this could be the rate of water as it flows into a bucket, the rate of sand as it spills onto the floor, or even something as a ladder falling against a wall. So we're going to go ahead and start with looking at rate of change without any real life application. We are starting with w is equal to x squared plus y to the fourth power. We want to find this rate in terms of time. So we want to go ahead and find d dt of this equation implicitly. We're looking for the rate of change over time. So we're going to take the rate of change of w, of x, and of y to the fourth, of d dt. Now, when I take d dt of w, implicitly, that gives me dw dt. The derivative of w is just 1. Now that is equal to, again, this is d dt of x. So that leaves me with dx over dt. And then the derivative of x squared is 2x. And the last one, and again, we are taking y, and we want the rate of change with respect to time, and that leaves us with dy over dt of the derivative of y, which is just 4y to the third power. Now, this is solved for dw dt. If I ask you to find dw for dt, given that I know x is equal to 3, that dx dt is equal to 2, that y is equal to 1, and dy over dt is equal to 4, I just go back through and substitute that. So wherever I have x is equal to 3, x becomes 3. Wherever you have dx dt, I know that is 2, so dx dt gets replaced with 2. Then I also know that y is equal to 1. So I replace y with 1 there, and that is 1 to the third power. And the last one, we're going to replace dy dt with 4. Now if I go through and multiply all of that out, I have 2 times 6 plus 4 times 1 cubed, which is 1, times another 4, and all of that is going to equal 28. We're going to practice one more time. Now I have w is equal to x squared times y to the fourth. And again, we're just going to take, and I want to find the derivative with respect to time for this. I want to practice the implicit differentiation before we move on. So this is going to be d dt, but when I take d dt here, I'm going to need to use the product rule. So starting with the first term, the derivative of w with respect to t, that just gives me dw dt. the derivative of w is 1. Now I need to use a product rule. The product rule tells me that I need d dt of x squared times y to the fourth plus x squared times d dt of y to the fourth. I haven't taken the derivative of that yet. Now, alternately, you could also use UV notation. That leaves me with dw dt is equal to the derivative of x squared with respect to t. That gives me dx over dt. The derivative of x squared is 2x times y to the fourth power. Now for the second one, that is x squared, and then the derivative of y to the fourth with respect to t. That gives me dy over dt, and then the derivative of y itself is 4y to the third power, which gives me dw over dt is equal to 2xy to the fourth dx dt plus 4x squared y to the third dy dt. Now I just want to make sure I also do this one more time, showing you how to get this with a UV notation, if that is how you prefer to go through and set this up. I say that v is equal to x squared. The derivative of v is going to be 2x, but I want this again with respect to t, so I need to have the dx dt. Now for the second part of the product rule, I have that u is equal to y to the fourth, so the derivative of that is 4y to the third, but again, I want this as with respect to t, so that is why you need the dy dt. I want the derivative with respect to time, but my variable is not time, my variable is y, so this is the derivative of y with respect to t. And if you see what I have, when I would multiply that together, that 2x times this matches up with my first portion, and then the second portion matches up here. All right, so I'm going to start by looking for three things here. I want to know what our given information is. I also want to know what is our known information. And I want to know what we're looking for. What are we trying to find? All right, so we'll go ahead and start with the fact that we have a radius of 50 feet. Our known information is the fact that we have a circle. And what do we know about the circle? We know a few things. We know that the area of a circle is pi r squared. We know that the circumference of a circle is 2 pi r. And we also know that the diameter of a circle is twice the radius. And the last thing is what we're trying to go ahead and find. And what we're trying to find is the rate of change of the area at the instant the radius is 10 feet. So what that does that mean we're trying to find? We're trying to find dA at a certain time. All right, there's one more thing in here that we need that's really important, and that is that the radius begins decreasing at 2 feet per minute. What that tells us is that the rate of the radius is decreasing over time at 2 feet per minute. Now we have all of the information out of this. The only thing that we haven't written down yet is that we want to know what happens at exactly, it looks like I did forget one thing. The one thing we also need to know here is that what we're looking for, what we're trying to find, is the rate of change of the area, but it happens when we know that the radius is equal to 10, because that's going to be different for different radiuses. All right, so since what we're trying to find is dA dt, we're going to use the area formula for the circle, which I know the area is equal to pi r squared. Let's go ahead and take these and take d dt of both sides. That will go ahead and give us dA over dt is equal to, now remember pi is a constant, and this is with respect to r, so that gives us dr over dt times pi times 2r. And again, we're taking the derivative of the inside. So I'm taking the derivative of this, and that is just coming down, and that is where I get the 2r times pi. Now I go back and plug all the information in. I want to know what happens when the radius is 10, so I replace the radius with 10. dr dt is 2 feet per minute. So now I know that dA dt, when the circle is decreasing, so dr dt we found, make sure you include that negative. So that's going to be a negative 2 feet per second, per minute. Now I multiply that times pi times 2 and times our radius, which is 10 feet. And all of that leaves us with dA dt, which is the rate of change of the area with respect to time, and that leaves us with negative 40 pi. I have feet squared per